on Friday, we started talking about the atom, and we looked at our proton, neutron, and electron. We talked about experiments that allowed us to figure out what was there. And we know now that the atom is made up of protons, electrons, and neutrons, and we know our protons have a relative positive one charge, our electrons have a relative negative one charge, and our neutrons are neutral, so they have zero charge. Now remember, this isn't a charge that has a unit with it because it's relative, to make it easier for us to understand. We also know our protons and our neutrons have a relative mass unit, AMU, of 1, whereas our electrons are so small that its mass is negligible. So while it does have a relative mass unit of 0.00055, we usually don't consider our electron mass and our mass of our atom. So knowing these things, we can figure out what's in our atom. But before that, let's talk a little bit about how our molecule or our atoms are shown on the periodic table, what kind of symbols we use. And the first thing we're going to talk about is the atomic number. So all atoms of the same element have the same number of protons. The number of protons never change. That is inherent to each atom. And if the number of protons does change, then you have a different atom. So we represent that as the atomic number, and that indicates the number of protons in an atom. In the periodic table, our atoms are arranged in increasing atomic number. And we're going to talk about the periodic table and the trends that we have on the periodic table in detail later on in the semester, but we'll talk about the periodic table a little bit. We might get to it today. We'll definitely get to it by Wednesday. So our atomic number is located on the top above our symbol of our atom on the periodic table. Each element has a unique name and symbol, and the symbol is either 1 or 2 letters, a capital letter, or 1 letter and a lowercase, or what we see commonly. For example, this is carbon, and it's represented by a C. And when we show our molecules and when we start drawing compounds, we'll be using those symbols. It's not necessary that you memorize all the symbols on the periodic table for now, but the ones that we'll use a lot, you'll know them by the end of the semester for sure. And it's really not really something you have to memorize, you'll just learn it. So that's what our little square on the periodic table symbolizes. So answering this question from last time, our proton tells us our identity of the element. If we know the atomic number, we can figure out the element name by looking on the periodic table. If we know the element's name, we know the atomic number, and we know the number of protons. So by just knowing that one thing, we can figure out what else is happening. So a question like this, there's a couple of things we need to talk about before we can answer them. But if we know our protons, and that means that we know a lot of things about our element already. Oh, I have another one as well. 2 in a row. Is this all big enough for you guys in the back? You can see the 247? Okay. I try to make them big to make sure you can see the iClicker questions. Now our number of neutrons is not specifically shown in this square. But we can determine our number of neutrons by looking at our mass number. Because remember, the mass of our element is based on the number of protons and the number of neutrons. So if we know what the mass is and we know the number of protons, then we can figure out our number of neutrons. To figure out our mass, if we look at the periodic table, that's going to be designated as a number under the symbol on our square. And sometimes it's a little bit to the right, but either way, it's under our symbol. This is our average atomic mass. We're going to discuss that a little bit later in the chapter, why this is 12.01 and not 12. And we're going to get to that today. But that is our mass. So of course, if we know our number of protons, which we'll know as long as we know which element we have, we can figure out our number of neutrons. So if our mass is 12 of carbon and we have 6 protons, how many neutrons do we have? We have 6, because the total number of neutrons plus protons gives us our mass number. So our mass number is equal to our number of protons and our number of neutrons. If we know 2 of these, we can figure out the other one. If we know our number of protons and our number of neutrons, we can figure out our mass number. And of course, we can always, as long as we know our protons, we can know a lot about our atom. Another notation is our symbolic notation. You'll see it sometimes. It's very similar to this, but slightly different. Oftentimes, we'll show our carbons written in this symbol. This is on the periodic table, but you'll see this written in a book or in a sentence, things like that. So in the symbolic notation, again, we have our mass number, but that's written on top, our atomic number, which is written on the bottom, and our atomic symbol. But you can't ever really get confused because you can't have more protons than your mass. So clearly your mass number is the bigger number. Because you can't have a mass that is lower than your atomic number. Because your number of protons does go to your mass. Now your number of protons can equal your mass number, like in some isotopes of hydrogen. Hydrogen, not all hydrogen have neutrons. So that can be true, but your mass number is always the bigger number. So if you kind of forget how this is, you can just think a little bit common sense wise. If you know your protons and your neutrons equal your mass number, clearly your mass is your bigger number. So that brings us to that mass. Here this mass number is written as 12, but on the periodic table we have 12.01. So where is that coming from and what's that difference? And the main difference of that is the fact that though our atoms, if they're the same element, always have the same number of protons, they do not necessarily have to have the same number of neutrons. And that comes to what we call isotopes. So it was discovered that some elements have different numbers or different masses. And for example, let's look at chlorine. In nature, there's 2 isotopes of chlorine that are found. One is a mass of about 35 atomic mass units, and the other is a mass of about 37. Now again, if it's chlorine, the number of protons cannot change. That is based on, if you look up on the periodic table, it's 17. That is our number of protons if it's chlorine. If it's not 17 protons, it's not chlorine. So the difference has to be in the neutrons. And that's what we see with isotopes. So our observed mass in the periodic table is our weighted average of all the naturally occurring isotopes. And what I mean by weighted is, if in nature we had 50% atoms being chlorine 35 and 50% atoms being chlorine 37, our mass on our periodic table would be just the average of 35 and 37. But that's not normal. Most of the time, one isotope is much more common than the other, so that's going to contribute to our mass in the periodic table more. For example, there are 2 isotopes of carbon, carbon 12 and carbon 13, and carbon 14. Carbon 14 is so small it doesn't contribute. If you look at the average mass in the periodic table of carbon is 12.01, which tells you that the most abundant isotope of carbon is carbon-12 because it weighs to the average more. Very commonly, like your tests contribute more to your final grade than your homework. Though your homework still contributes, your tests contribute more. So it's that concept of weighted average. And in fact, by looking at the periodic table, if the atomic mass in the periodic table of chlorine is 35.45, which of these two is in more abundance, chlorine 35 or chlorine 37? 35, because our average is closer to 35 than it is to 37. And the more that you have your mass average to be in the middle, that means the more that those two isotopes are in equal abundance. But I don't think there's any that are 50-50. And some atoms have more than just one isotope. They all contribute to our average. But all isotopes, again, have the same number of protons. That's really important. So our different mass numbers have to come from the neutrons. So our atomic number is based on our number of protons, and I'm just going to call that Z for now. And our mass number is our protons plus our neutrons, and that's going to be a whole number when we're talking about a specific isotope. If we're talking about our element in nature of all isotopes average, it's often going to be a decimal point. So our abundance is the relative amount found in nature. So oftentimes our isotopes are written with our chemical symbol or the full name, and then the mass number. For example, as I've been talking about carbon-12, that's the way it's usually designated, carbon and a 12 or C12 versus carbon-13 or C13. So that's how we designate those. Also, you might see it written as this chemical symbol with our mass number on the top and the atomic number on the bottom, the symbol I showed a second ago. So for example, again, carbon-12, carbon-13, and carbon-14 are all exist in nature, but carbon-12 is our most abundant, and we see that by our average being 12.01. So that's how we show these. And we might also show it as carbon-12, carbon-13, or carbon-14 written in this way. So if we know these symbols, we can figure out our number of protons, neutrons, and electrons in our atoms if we're given them. So for example, we have these three isotopes of nitrogen, nitrogen 15, nitrogen 14, and nitrogen 16. And we are given, of course, our atomic number, which is 7. We can also look that up in the periodic table if we knew we were talking about nitrogen. So if we were just written nitrogen 15 out, you could still figure out your number of protons, because we could always look on the periodic table for them. And on quizzes and exams where we're using the periodic table, I will be providing you with a periodic table. You will not be bringing your own periodic table. So I'll provide that for you. But you will be provided with a periodic table. You do not need to memorize it. That's not really important. Okay, so looking at this one, first off, our solution to this is the number of protons, pretty easy. It's all nitrogen, so it all has the same number of protons, and that's based on our atomic number. So they all have 7 protons, fairly straightforward. But our number of neutrons is going to be different. Also, our number of electrons, if these are all neutral atoms, how many electrons do they have? 7. If it's neutral, they're all going to have 7 electrons because we have to have the same amount of protons and electrons, so their charges cancel out and we have 0 charge. So they all have 7 electrons, assuming they're all neutral atoms. And if they weren't neutral, there would be a specific symbol that we show. And I'll show this in a couple of slides. But our main difference between these three are the neutrons. So we can figure that out by subtracting our mass number, which is given as our top number, from our number of protons. So for A, we have 15 mass. And again, we have 7 protons, so we must have 8 neutrons. For B, we have 17, so we have 7 neutrons. And for C, we have 16, so 16 minus 7 is 9 neutrons. So that's how we can figure this out, and we can figure that out for any isotope, as long as we know which symbol it is and what mass we have. So looking at this example, we have chlorine with a mass of 37, and again our atomic number is 17. So this is asking for our amount of neutrons. Now we have how many protons? 17. Our mass number is, oops, that's 20. Our protons is 17. This isn't asking for electrons, but if it's neutral, how many electrons? 17. So as far as our neutrons, we know our mass number is 37. And our mass number is equal to our protons plus our neutrons. So our neutrons is going to be equal to 37 minus 17. And that's, of course, 20. Fairly straightforward math for this. So as long as you know the symbol or you know a couple of things about the atom, we can figure out the rest of the things about the atom. For example, we have this. So first off, we're starting with the symbol carbon-13 and 6, and we're told that the number of protons is 6, and the number of neutrons is 7. So how many electrons do we have? 6, because our electrons have to cancel out if these are neutral. So what's our atomic number? 6. It's based on our number of protons, not the number of electrons, and that'll be important in the next couple of slides. And our mass number, of course, 13, the symbol's given, or we can take our 6 plus our 7. Looking at the next example, we're given our electrons and our mass number. How many protons? 42. There's two ways we know that. One is we know our number of electrons, and two, we know our chemical symbol. As long as we know our chemical symbol, we know our number of protons. So we have our mass number, and of course we know our atomic number is 42. But how many neutrons do we have? 54. 96 minus our 42. Again, when we're looking at aluminum, here, what is our protons? 13, and that's also our atomic number, and that's based on this number. Our electrons, I went to my mass number next, sorry. My mass number is given as 27, and my electrons are 13. So by knowing that, we can figure out our number of neutrons, 14, which is going to be 27 minus 13. Lastly, for cesium, what's the number of protons and our atomic number? That's the same. And what's our number of electrons? And lastly, what's our number of neutrons? 78. 133 minus 55. So if we just know a little bit, we can figure out a lot about our atoms. Looking at this one, we have curium-247, and of course our atomic number is 96. So if it's neutral, we have 96 neutrons and 96 electrons. But we have 151 neutrons. So we've kind of beaten that dead horse. You should know how to do that now. Now when a chemical reacts, though, something's got to change about the element. It can't be still in its elemental form when it reacts. And we've already said that our number of protons does not change. So in a chemical reaction, what's happening? So according to Dalton's atomic theory, statement 4, when our elements undergo chemical reactions, the reactant elements don't turn into other elements. So they're not turning into other elements. With the exception of nuclear chemistry, that's true. And we're not really getting into nuclear chemistry in this class, though you can imagine nuclear chemistry is taking place where? In the nucleus, or has something to do with the nucleus. But in most chemistry, in our organic chemistry, inorganic chemistry, forming salts, things like that, we'll be looking at something else. And that's mostly the movement of some of the subatomic particles called our electrons. So something has to be changing in the reaction because the same atoms are present, but somehow our atoms are rearranging. or something's happening. And if the number of protons isn't changing, because that would change the actual atom, then something else has to be changing. So what's often occurring is somehow the transferring or sharing of electrons. And that's what most of chemistry is studying, again, with the exception of nuclear chemistry. We're typically looking at electrons, either how they are given up, how they're accepted, or how they are shared. And in this class, we're mostly going to be looking at how they are transferred, but we'll sometimes look a little bit at how they're shared and talk about those types of bonding. So what we're looking at is the changing of electrons, and that's key. Remember, the proton won't ever change. So what happens if we lose electrons? If we lose electrons, that's going to change our charge. Our charge no longer will be neutral. We're going to have a positive charge. And if we gain electrons, what's going to happen? We're going to have a negative charge. And the key to this, so you don't get confused, is always to remember electrons are negative. So to figure out what charge you have, always think about how many electrons do I have relative to my protons. So we're going to look at that. First, we're going to talk about a little bit of terminology. Try not to put the answers too low, but for those of you in the back, D says all of the statements above are true, in case you can't see it. So a little bit of terminology. First, when our charged particles, we form charged particles whether we are losing or gaining electrons. Remember, we're not changing the amount of protons. And in most of these reactions, we're not changing the amount of neutrons. Again, that would be nuclear chemistry. So we're really only working with our electrons. So those are called ions. As soon as our atom has a charge, we call that an ion. If we gain electrons, so therefore our charge is negative, we call that an anion. And you should know that terminology. That is one that we will use often. If, however, we lose electrons, our overall charge is going to be positive, and that's going to be called a cation, or cation. But I just kind of drew that out. So our cations have positive charge, our anions have negative charge. The amount of positive charge and negative charge is dependent on how many electrons were gained or lost. And we'll learn throughout the class that it'll be dependent on how many electrons are in our outer level of our outer energy level. But we'll really get into that in chapters 7 and 8 and 9. So we'll really look at that a bit more later. So for this one, our statement that's true, the gain or loss of an electron will result in an ion. It's cold. So just like before, if we know a little bit about our atom, we can determine our number of protons, neutrons, and electrons. But now, if we have a charge, we have our protons and our neutrons will not change, but the amount of electrons will change. And again, to remember how to do this, to double check yourself, always remind yourself electrons are negative. So if you have more electrons, your charge is going to be negative. So for this example, copper has a positive 2 charge, so I'm going to have more protons than electrons, because protons are positive. So let's look at that. First off, before we get into some of those calculations, I want you to understand that ions are behaving differently than our neutral atoms. And some ions are way more stable in their ionic state than they are in their elemental state. For example, sodium chloride is just table salt. It's found everywhere. You ingest it all the time, which means you're ingesting chloride ions. You're ingesting sodium. Sodium's really what our body uses for our ion pumps, but you're also ingesting chlorine. That's also an ion that we use. However, if you're in the presence of chlorine gas, that's very toxic. A hugely different concept. So just because something, a chemical, has the same elements in it does not mean it's going to behave the same way. And different forms of different elements have different behaviors. So ionic forms absolutely have different behaviors. Sodium chloride is fairly stable. It's non-reactive. It can dissolve in water. We use it. We eat it. You don't want to eat it in moderation, but still, we come into contact with it all the time. Typically, in sodium chloride in our solid form of sodium chloride, our sodium ions are interacting with our chlorine ions, and overall our molecule, sodium chloride, is neutral. And it balances each other out by our positive charge of our sodium ions balancing with our negative charge of our chlorine ions. And we'll get into that in more detail. And then we can dissolve it in water by pulling those ions apart. Positive ions and negative ions are always going to be attracted to each other, just like mini magnets. So, let's talk a little bit about atomic structure. Nonmetals form anions. For each negative charge, the ion has one more electron than the neutral atom. Because remember, each electron, we give it a relative charge of -1. So while the amount of protons and electrons that are equal cancel out, if we have extra electrons, that's going to give it charge. And we're going to talk about why later on nonmetals form anions. And we're going to look in detail why that is. But for example, chlorine, when it's neutral, has a 17 protons and 17 electrons. But our ion, which is fluorine negative, and notice that we will put the symbol, here's our symbol for fluorine, and then we put our charge as a superscript. Now, we don't typically show the 1, and that'll be a common theme throughout our chemistry, that we won't show a 1. So, it shows a negative, that's implied it has a -1 charge. So that means it still has 17 protons. Remember, that never changes. But it has 18 electrons. It has one more. If we look at phosphorus, phosphorus likes to form a -3 charge. Now notice when it's drawn in the superscript, it's a 3 negative, not -3. I'm not really sure why, but that's how it's designated. I'm sure there's a good reason for it. So we do show anything that's not a 1. In the neutral state, our phosphorus has 15 protons. You can find that by looking on the periodic table to find its atomic number. So that means it has 15 electrons. But when it has our anion, then it must have 18 electrons. So it has that 3 negative charge. Anions are named by changing the ending of the name to IDE. So instead of fluorine, which is what you'll see if you look up the name on the periodic table for neutral fluorine, it's going to be the fluoride ion. And then we just throw ion on the end. So for example, chloride, ion, chlorine, plus 1 electron is going to give us our chloride ion. This is what it looks like. And again, our symbol is going to be Cl negative. And then we don't show the 1. Oxygen likes to form a -2. And again, we'll talk about why later on. But it accepts 2 electrons, so it forms an oxide ion. Now metals form cations. They like to give up electrons. And again, we'll talk about why later on. So for each positive charge, the ion has one less electron. Not one more proton, because remember, the protons never change. So it has one more proton than electrons. But to do that, it has to lose an electron. Because remember, the protons never change. That stays the same. So for example, sodium atom has 11 protons and 11 electrons, but our sodium ion has 11 protons. Again, protons aren't changing, but now it has only 10 electrons. You can always double check by adding them together. You know that you have positive 11 plus negative 10. That should give you positive 1. Again, notice the positive and the symbol, and we don't show the 1 when it's only a 1. If we look at calcium, it likes to form a positive 2, so notice we will show the 2, and then the plus after it. And that means it has only 18 electrons. Cations are named the same as the metal, except we put ion on the end. So sodium, when it loses its electron, it forms a sodium ion. So nothing changes about the name except we put ion on the end. And same thing here, calcium would be calcium ion. So if we know a couple of things, we can figure out our atom. So for example, we're not given the atom in this case, but we have the atomic number. The atomic number is 16. You don't have to memorize what atomic number goes with what atom, though. Carbon's one you'll remember. There's a lot that you'll remember, but you'll have a periodic table. So if we look on the periodic table, that means we have 16 protons, and if we look on the periodic table, that means it's sulfur. Because remember, the atomic number dictates what element we have. But we're not finished with that ionic symbol, because notice we have 16 protons, but we have 18 electrons. So we have a charge which we need to specify in our ion symbol. So what's our ion charge? We have a 2 minus because we have 16 positively charged protons and 18 negatively charged electrons. So that's a 2 minus, and we will designate that as a superscript in our ion symbol. Now looking at the next one, again, we don't have the ion symbol, but we're given our protons, so what's our atomic number? 12. So if we know that, then we know our ion symbol. Now don't say this is carbon. Carbon's mass is 12. That's a common mistake because everyone thinks carbon 12. Our atomic number is our number of protons. So that's actually, if we look on the periodic table, Mg, magnesium. So it has a 2 plus. So if it has a plus, do we have more or less electrons? Less. So how many electrons do we have? 10. Because we have 2 less. Looking at aluminum, first off, we are told we have a 3 plus charge, and we're told it's aluminum. So to find our number of protons, that's easy. All we have to do is look at the periodic table. If you have one in front of you, what's the atomic number? It's 13. Don't worry, you have a periodic table on your test or quizzes. You don't need to memorize these. So we know our number of protons. We know our charge is 3 plus. So how do we have more or less electrons? Less. Because, again, we have a positive charge. So that'll be 10. Lastly, we have bromine. We know we have a -1. Our ion charge is -1. And I don't know why this chart is telling you we have 36 electrons, but if we didn't know it was bromine and we knew we had 36 electrons, we could figure out the number of protons. But of course, it's going to be 35. That's fairly easy. We didn't have to do any math, but you could always double check yourself. Because we know it's bromine, so we can look on the periodic table and determine the atomic number. But we can always double check. We have more electrons, 1 more electron than protons, so that makes sense. It's 1 minus. You could always double check as well, because again, nonmetals form anions. So our nonmetals, bromine and sulfur, they both have a negative charge. Metals form cations, and our 2 metals on here, magnesium and aluminum, both have a positive charge. There's a couple of ways you can double check yourself when you're doing a test or a quiz or your homework. So looking at this one, we have copper 64, and we have a 2 plus charge. So first off, we do not have, and it's not a choice, but just so you don't confuse yourself, we do not have 64 protons. That's the mass. So we could use that to figure out our neutrons. The amount of protons we have is dependent on the periodic table. So if we look at the periodic table of copper, we have 29 protons. So we can figure out our neutrons by taking our mass 64 and subtracting our 29 protons. Now don't subtract the electrons because the electrons don't contribute to the mass. To determine our electrons, we know our charge, we know it's a metal, so we know we'll have less electrons, and based on the fact we have a 2 plus charge, we know we have 2 less electrons. So that's 27. If you ever get confused, don't try to memorize this. All you need to know is electrons are negative, so you can figure this out because you know how to add positive and negative numbers. So as long as you remember that, you don't have to memorize a formula that your charge equals your electrons versus your protons. But it's true, it does. So like I said, we've been talking about the periodic table. The periodic table is ordered in a way that the periodic table is very, very useful for a chemist. We can predict a lot of things about our atoms, our reactivity, and how our molecules behave based on the periodic table. And the periodic table is ordered elements by their pattern of properties and their atomic mass. And they're really measured or listed by their atomic number. And what Mendeleev, who's the one who really came up with the periodic table, found was that there was a repeating pattern of properties. And we're going to talk about in chapter 7 where that repeating pattern comes from and why the periodic table works the way that it's put out. And we're going to look at that. So periodic law says that when the elements are arranged in order of increasing atomic mass, certain set of properties recur periodically, hence periodic table. Just the fact that we see these properties recurring. So pure elements that are in the same column have similar properties. And that's what we see over and over again. And we can use these patterns to predict properties of undiscovered elements. That's how we kind of have some squares that are there that we're like, we know these undiscovered elements, how they behave, even though we haven't actually observed them based on these properties. Where atomic mass order does not fit other properties, he reordered by some other types of properties. And we'll see that by those lanthanides at the bottom of the periodic table. So, for example, Te and I don't really behave the way we would expect. And again, there are reasons for that. So, if we just have these first 20 just written out, an increasing atomic number, hydrogen has a atomic number of 1. Its mass is typically 1.00 something. So how many neutrons does hydrogen, our most abundant isotope of hydrogen, have? 0. So hydrogen has 1 electron, 1 proton when it's neutral, and 0 neutrons. Now we also have, that's our hydrogen 1. We also have hydrogen 2 and hydrogen 3, which are called deuterium and tritium. But they're not very abundant. But they have more neutrons. But hydrogen, in its most abundant isotope, doesn't have any neutrons. All the rest of them have neutrons, of course. So if we draw them this way, the color coding shows that hydrogen behaves, we have some repeating patterns. And we see helium behaves very similar to neon, lithium behaves very similar to sodium, and so on. And that's how these were put together in the periodic table, like this. Now, of course, the periodic table is much bigger than this, but at the time, he didn't have that many elements. Elements with similar properties fall into the same column. Hydrogen's a little odd, because notice it's shown the same color as fluorine and chlorine, and it behaves a lot similarly to fluorine and chlorine in some ways. It has some properties very similar to carbon, and hydrogen can actually form a negative ion or a positive ion, depending in what kind of environment it's in. So hydrogen's a little weird, but for the most case, we see some repeating properties. So we'll talk a little bit about how the periodic table is set up. And later on, we're going to really delve into these. We're not really going to get into the trends so much in this chapter, but we're really going to delve into the trends later. Like I said, hydrogen's odd. We put it here based on its mass and its size, but it actually is a nonmetal and considered a nonmetal, which is typically the things over there. We have metalloids and metals. And again, you don't have to memorize this, but there's some things about it that you will have to know how to read the periodic table. So solids are metals, which are all these things in blue. We have a lot of them. Now, not all metals are the same, and we'll break this down further later on. Metals tend to have similar properties. They tend to be solids at room temperature, except mercury. Everyone's seen mercury thermometer. Mercury is a liquid at room temperature. They have typically a reflective surface. They're shiny. They tend to conduct heat very well. Of course, their conductivity can vary. Aluminum doesn't conduct the same way as other metals, so conductivity can vary. They also conduct electricity, which is why you want to be careful around metals and lightning. They can be shaped. Again, not all metals are as malleable as other metals. We know gold is very malleable. We can make it into jewelry fairly simply, whereas other metals may not be as malleable. If I were to bring in sodium metal, it's easy to cut sodium metal with a string, really, if it doesn't catch on fire from the air first. But it's very reactive. But it's still going to be shiny, and it still can be shaped. So they're not all exactly the same, but they have similar properties. They're ductile, meaning we can draw them into wire. They lose electrons, so they form cations in reactions. And about 75% of the elements are metals. So as you can see with all the blue squares. We have nonmetals. There's not that many nonmetals relative to metals, but really organic chemistry, which is the study of carbon-containing compounds, is really the study of how nonmetals bind to each other that contain carbon. And there's a lot of organic compounds, and I teach 2 semesters of organic chemistry, plus sometimes intermediate, plus sometimes advanced. And I did my PhD in organic chemistry, which is another 5 years. So just because there's not as many nonmetals doesn't mean that the way that they can react are small. There's a lot of ways that they can react. So they're found in all 3 states typically, meaning, for example, sulfur is often found as a solid, a nice yellow solidy material. And if you do spill mercury, the way that you can clean it up is by putting elemental sulfur on it, and it binds really strongly to mercury. Bromine and chlorine, however, chlorine, Cl2 in its elemental form forms a gas, again very toxic. Bromine in its elemental form is typically a liquid. So we have different states they can exist, depending on what form they're in. They often tend to be poor conductors of heat. They're poor conductors of electricity. They're typically, the solids are brittle in most cases. And they like to gain electrons in reactions and typically become anions. So except hydrogen, we're talking about the upper right-hand side of the periodic table. The last main consideration, again, we'll break up metals more later, but the third is our metalloids. Metalloids kind of follow that zigzaggy line that we show in the periodic table, and they're shown in the purple squares in this figure. They show properties of metals and some nonmetals. So for example, silicone is shiny. It conducts electricity, but it doesn't conduct heat well, and it tends to be brittle, whereas most metals are in brittle solids. So that's a more non-metal thing. So that's why they're metalloids. They kind of have properties of both. Oftentimes they're known as semiconductors, meaning they can conduct some things like electricity, but they don't conduct heat well, or vice versa. So those are just our general breaking down of the periodic table. So within those, not all metals behave the same. Not all nonmetals behave the same. So within those, each column every atom in a column tend to have similar properties. They're not exactly the same, and again, later on we'll really break this down, but they tend to be very similar. There we go. So columns are called groups or families on the periodic table, and they're designated by a number and a letter on the top of the periodic table. Rows are called periods, and each period also shows a pattern of properties, but it's a pattern of repeating properties, which we'll see later on as well. So our main group elements are represented as 8 groups, and our main group elements are what we'll talk about mostly in things like organic chemistry. We don't really talk too much about our non-main group elements too much there, except for catalysts. Transition elements are B groups. All the transition elements are metals. The main group elements have both metals and non-metals as part of it. And then our bottom rows are our intertransition elements and our rare earth elements. They're metals. They really belong to periods 6 and 7, but we put them at the bottom of the periodic table. So here's the periodic table so we can see this. So our main group elements are A, this is 1A, 2A, 3A, 4A, 5A, 6A, 7A, and 8A. And notice they contain both metals and non-metals. So of our main group elements, we have some families. We have our alkali metals. Notice, even though hydrogen is on top of here, it doesn't quite behave like those. What we'll see is sodium, potassium, they behave very similarly. They're both very reactive. They both look very similar metals. They do have some differences in their chemical behavior, but that's typically because they have different sizes. And we'll learn later that our size increases as we go down the periodic table. If I were to bring sodium metal in here and put it in water, it would catch on fire. If I bring potassium metal in here and put it in water, it would also catch on fire. They both form ions of a positive 1 charge. So they have a lot of the same properties. So those are our alkali metals. Then here is our that was our alkali earth metals. These are our alkali metals. Yeah, these are earth metals, sorry. And these are things like calcium, and we'll look at those in more detail later. And again, these are still main group. These, I don't know why my thing does this. These are our transition metals. And these would all be B group. Now they're all metals. And we'll call them transition metals because they can form varying charges. What we'll see is these typically only form a positive 1 charge. These only form a positive 2 charge. But these have different charges that they can form. That's why they're transition. And we'll look at that more later. In red, we have our noble gases. We'll learn that these don't react very well. We call them inert gases often. And these are also part of our main group. We have our halogens in pink. Halogens are also going to be a very important group. Now, these aren't really designated as anything, and as far as naming our families, but they are still very important. And then way at the bottom, we have our lanthanides, and these guys are acetonides. And these are really 6 and 7, but they kind of behave very differently. So they're our other group. They're not our A or B. So as you can see, we have 1A, 2A, 3A, 4A, 5A, 6A, 7A, and 8A. Those are our main groups. Our transition metals are our B. And these aren't showing our other groups because often we won't really be looking at those too much. So if we're looking at this, you should be able to answer this question fairly easily. I really could make the periodic table bigger. You could always have your own periodic table during class for when I ask questions like this. So if we're looking at this one and we're figuring out which of these are most similar to 10, which is over here, of these ones that we're given, what we see is that lead, which is right here, 82, is in that same column. So that means it's probably pretty similar to our 10. And that's how we can use our periodic table to determine similarities. So we're going to stop here today, and we will continue on Wednesday. Remember, quiz is going to be Friday. And have a good day, and check Moodle for all those announcements that I gave you.